0, 1 is 1 point, 1, 0 is 1 point, and 1, 1 is 1 point. So how many did you get? So you get basically n squared, which is 2 times 2 squared, which is 4 points. So you will get 4 values. So if you have n equals 100x coordinates and y equals 100 y coordinates, number of values that you get in this f vector is going to be n squared, which is 100 squared, which is 10,000. Okay? And I gave this theory, mesh grid. You will be using the method called mesh grid and mesh grid. And when you utilize this function, you will realize it will generate n squared points. Okay? You will realize it is going to be n squared points. So now I talked about plotting. Now let's talk about the effect of rho, which is the correlation coefficient. How x and y relationship, how x and y they are correlated. How if I increase x, how y will behave. What will be the behavior of y? Now, because it is a 3D, it is a 2D function of 2 variables, and the value is going to be in the z direction. Okay. This rho, when it is negative, do you see that it is orienting this way? Slope is going to be negative. Slope is negative. Is orienting this way. Now, down the line, I actually drew many figures like this with different rows, and I will show you another plot. This is another example. Do you see rho equals positive? You see that in this case, rho is orienting this way. If rho is negative, this entire 3D plot will orient. You see that? That is the effect of rho, and this rho is called correlation coefficient. Now let's talk about this example. So we are here to find the marginal figures of random variable x and y. So solution. So given f sub x comma y, taking value x, y, which is given this expression, I want to find what is f sub x, comma x equals what, and f sub y, comma y equals. Okay? So the formula here is you just write down, I'm going to use different color, f sub x, and then in parentheses we have x equals, you integrate out negative infinity to positive infinity. You have f sub x comma y, taking value x, y, okay? And you integrate out, you just make the variable y disappear. So now you just substitute negative infinity to positive infinity, and you go, you have 1 over 2 pi square root over 1 minus rho squared e to the negative half, and then we have x squared minus 2 rho xy plus y squared over 1 minus rho squared. Now you integrate out y. So if you integrate out y, you will be left with simply function of x. So that's why you get the function of x. So you go through the integration. I'm not going to go through the integration. You use Gaussian relationship, Gaussian integral, that formula. You go all the way, and eventually you will end up with expression. I'm going to write down f sub x, one more line. 1 over 2 pi square root over 1 minus rho squared, and then e to the negative x squared over 2, and we will have integration negative infinity to positive infinity. You have e to the negative half y minus rho x squared over 1 minus rho squared dy. Now you can see this part using Gaussian integral. Using Gaussian integral, you will see this part using, again I'm using Gaussian integral from chapter 4. Gaussian integral, we have this part is basically square root over 2 pi, and you have 1 minus rho squared. So if you have 1 minus, this part gives you square root over 2 pi, 1 minus rho squared. So you will see here 1 minus 2 pi square root over 1 minus rho squared, and then this part becomes, using Gaussian integral, 2 pi 1 minus rho squared. Okay. So here you have square root over 2 pi, here you have total 2 pi. Here you have square root over, no, here I missed one term, which is 1 e to the negative x squared by 2 over 2. So this, then in the denominator you will have square root over 2 pi. So here you will have square root over 2 pi, and then here you have square root over 1 minus rho squared. Here you have square root over 1 minus rho squared. These two guys will disappear. Now you are left with e to the negative x squared over 2. So this is the final answer. So f sub x is your final answer. Similarly, similarly, marginal PDF of random variable y given joint PDF f sub x comma y taking value x y is marginal PDF of random variable y is going to be function of y is 1 over 2 pi square root of 2 pi times 2 pi times square root over 1 minus rho squared, and then you will have e to the integration negative infinity to positive infinity e to the negative half x squared minus 2 rho xy plus y squared over 1 minus rho squared, and you integrate out x this time. So similarly, you would see this part will be 1 over 2 pi square root over 1 minus rho squared, and then this part is going to be e to the negative y squared over 2, and then you will see square root over 2 pi times 1 minus rho squared using Gaussian integral. Using Gaussian integral. So now, eventually, you will see that this 2 pi, square root over 2 pi, here you have 2 pi, you are left with square root over 2 pi, this is square root over 1 over rho squared, and 1 over rho squared disappear. You are left with 1 over square root over 2 pi e to the negative y squared. So this is your marginal PDF of random variable, random variable y. So this is another answer. So I did not go through that integral. I directly use the result from Gaussian integral. Now, if you simply plot x and y, so this 3D plot, boils down to 2D. 3D plot boils down to 2D using marginal PDF, and that I plotted right here. So this is the marginal PDF of random variable x. This is marginal PDF of random variable y that we got from joint PDF. Now, one thing that I would like you to note. Okay. Now, for one random variable x, guys, PDF, probability density function, PDF, f sub x between parentheses x is going to be 1 over square root over 2 pi sigma square root over 2 pi, and then e to the negative half x minus mu over sigma. Do you guys recall from chapter 4 this expression? Yes or no? You guys recall this expression from chapter 4? This is a Gaussian PDF with mean mu, which is expected value of x, with mu representing the expected value of x, which is basically mean, and variance sigma squared. Now, can you compare this equation and this equation? Can you see what is the mean and variance? So if you substitute mu equals 0, so and sigma squared equals 1, so you are left with mu equals 0, sigma equals 1, you are left with this expression. And because mu equals 0, sigma equals 1, the marginal PDF of, see how I interpret. So the marginal PDF of this joint PDF becomes a standard Gaussian variable with parameter 0, the parameter 0 and 1. So this becomes standard normal variable, the parameter 0 and 1. This becomes standard normal variable with parameter 0 and 1. So mu equals 0, here mu equals 0, variance sigma squared equals 1. And these are basically special case. And also the joint PDF, that 3D plot that we saw, this is also a special case of a generalized joint PDF that is part of the computer assignment. This is also a special case of generalized joint PDF. So generalized joint PDF, you will see yeah, you don't have to write down the expression. You will have this document. Okay. So generalized joint PDF. Yeah. Generalized joint PDF looks like this one. This is equation number 1 here. Okay. So here, if you substitute, guys. If you substitute sigma x equals 1, sigma y equals 1, and mu sub x equals 0, mu sub y equals 0, you will see that this equation boils down to this equation. So the equation, the joint PDF itself in example 5.18 itself is a special case of generalized joint PDF. So this version is very important. Some built-in functions, joint PDF functions actually implement this one. And you can shift, you can choose different mu and variance, and you can shift this joint PDF. You can shift the mean and variance of this joint PDF by choosing different mean and different variance of random variable x and y. Okay. So now, given we went through this example, now this topic would be the topics here pertaining to independence of two random variables. It's a piece of cake. If you have joint PMF, so this is joint PMF. Joint probability mass function for discrete random variable. If we can actually say that two discrete random variables are independent, they are independent if and only if this joint PDF is same as the multiplication of their marginal. The joint PMF is exactly equal to the multiplication of their marginal PMFs. So we went through marginal PMFs. I'm not going to explain anymore because these are already given. Here I have one example that directly applies to this equation. Look, guys. So I just took this example is not from the book, but I just created this example, taking the previous two die random experiment that we toss two die where order matters. If you do that, if order matters, we went through the fact that because order matters, we have total 42 outcomes. Two die, we have 6 sides, so total 42 outcomes instead of 36 outcomes because order matters. So that's why you have the joint PMF table looks like this. Joint PMF table looks like this. Now, here the first question, are the process of this random experiment independent? Yes or no? The question here is yes or no. Answer would be yes, either yes or no. Can you tell me right from here? Look at this equation. Right from this data we have, and we have equation for the joint PMF, equation for joint PMF of two random variables that would be independent if the joint PMF is the multiplication of marginal PMF. So, what is the answer? Yes or no? The answer is no. Answer is no. Why? Marginal PMF of random variable x, taking value, any value j equals 1, 2, 3, 4, okay? It is going to be 1 over 6. You can see we went through that already, marginal PMF. And similarly, marginal PMF of random variable y taking value k is going to be 1 over 6. Now, the joint PMF, we have joint PMF, random variable x comma y taking value j, k, is going to be for I not equal j, this is 1 over 46, 1 over 44, which is not equals 1 over 6 times 1 over 6, which is 1 over 36. This is not the case. You see that? So that is the reason the other equation is not satisfied. That is the reason here answer is no. Now, how can we determine, find the joint PMF if the independent process of two fair dies are conducted? So because in this case, I said that these are totally independent, which means that order doesn't matter. I just look at the number of dots on the top. So order doesn't matter. So in that case, instead of 42 outcomes, you will see 36 outcomes. So in that case, find the joint PMF. So joint PMF is going to look like this. Here answer is no. Here joint PMF. Joint PMF. Will look like this. So here j equals 1, j equals 2, dotted dotted. Here j equals 6, k equals 1, k equals 2, dotted dotted, k equals 6. Here now you will not have 42 outcomes, here you will have 36 outcomes. So here, the probability to join PMF is going to be 1 over 36, 1 over 36, and so on, 1 over 36. So all the way 1 over 36, 1 over 36. Okay? So joint PMF would look like this, and marginal PMF of random variable x taking value j is going to be 1 over 6 for j equals 1, 2, dotted dotted 6, and it is going to be PMF of random variable y taking value k is going to be 1 over 6 for k equals 1, 2, dotted dotted 6. And if you add them, 1 over 6 is going to be 1. So therefore, these are marginal PMFs, guaranteed. So this is the answer for the second part of the example. Now another example pertaining to, okay, if you want to take picture of those, you can take picture. So another example will have pertaining to the joint PDF. But in case you have joint CDF, so joint CDF formula is same. The joint CDF of two random variables x and y is going to be marginal CDF of random variable x times marginal CDF of random variable y. And you can guarantee, if this condition satisfies, you can guarantee that x and y will be independent. Same formula, similar formula for joint PDF. And this, I have a nice remark here. Independence means the joint behavior factorizes into two products of individual behavior. So marginal behavior of random variable x times marginal behavior of random variable y. So this is very, very important. So I added this remark this year's not much, this year's not. So now we will directly use this formula to solve this example. So this example, I actually took it again. I took it from the previous example. So we have the joint PDF. So joint PDF of two standard Gaussian random variables. Joint PDF of two standard Gaussian random variables x and y. So intentionally here, the plot that I'm showing you, intentionally, I wrote my code with rho equals positive 0.6 instead of negative. Just to highlight that this time my 3D plot, the joint PDF, is in the positive direction. Okay, instead of the other. So you can just control rho to make it different shape. Yeah, I actually plotted many of these when I was working for Defense Canada, Center for Operational Research and Analysis. So they use this sort of plot a lot. Actually, most the scientists that I work with, they are physicists. They got PhD from physics because it's an operational research team. Very like as an engineer plotting this sort of plot and analyzing, it was a piece of cake for me. So you will see down the line if you take some research position in different national lab pertaining to operations research or pertaining to probability statistics, random processes, many complex systems, then you would end up with plotting many of these 3D plots. Okay, and right from now, like, you should be able to click that, okay, which parameters I should take and what are the plots, what are the behavior that I would expect. So here, row I chose 0.6. Now the 3D plot aligned in the positive direction. Here, intentionally, I showed the x points, okay, x coordinates, so negative 2 to positive, negative 3 to positive 3 actually, and y negative 3 to positive 3. Question here is that find the condition under which random variable x and y are independent. Okay? Yeah, I will write down the conditions. So I will give you 5 minutes break. Let's take 5 minutes break and then we come back.